Thank you very much, Mike, for the brief introduction. And thank you very much once again for inviting me to give a talk on my topic, unraveling the variation in venom toxin composition for beauty species. So snake bite is a serious public health problem in many tropical and subtropical countries. This problem is mostly intense where human populations are engaged in agricultural activities. Unfortunately, public health authorities have given little attention to this problem. In sub-Saharan Africa, where I come from, it is estimated that venomous snakes bite about 1.2 million people every year, resulting to over 35,000 deaths and around 14,000 amputations. And according to the World Health Organization, this data is under-recorded. So some of the notable venomous snakes in sub-Saharan Africa include the Bitis carbonica, Bitis erectans, also known as African path adder, black mamba, and sawslet viper. So this research is actually focused on Bitis erectans because they are responsible for the vast envenomation in Africa due to their countrywide distribution. And so the research goals were to identify regional variants in Bitis erectans venoms, sampled from the wild in state of northern Nigeria, and also to develop small molecules with generic inhibition of specific toxin classes to circumvent the challenges associated with snake venom variants. And so in this research, Bitis erectans were sampled for the wild in state of northern Nigeria, as the Katsina states, the Yobe states, and the Gombe states. These states are hotspot zones for snake bites in Nigeria. And of course, Bitis erectans are responsible for over 90% of the snake bite cases reported in these localities every year. So to elucidate the possible differences in Bitis erectans venom composition, the snake venoms were actually subjected to SDH analysis and visual assessment of the gel revealed subtle and stark differences in protein binding patterns across the venom samples. That the separation patterns of the venoms by SDH afforded an overall preliminary picture of venom complexity and proteomic diversity. So since hemorrhage is the most significant pathophysiological effect of Bitis erectans, the hemorrhagic status of the venoms were evaluated in mice model. And as expected, all the venoms were hemorrhagic, and the different groups of mice displayed variance over time post-venom challenge. So panel A here is a representation of the hemorrhagic lesions observed after 4 hours of injection of the various venom from the Katsina state, panel B for the Yobe state, and panel C for the Gombe state. So in the Katsina state, one of the experimental mice injected with Katsina tree venom died after 30 minutes of venom injection, while the rest survived. In the Yobe state, all the experimental mice injected with Yobe 2 venom died after 30 minutes of venom injection. And lastly, in the Gombe state, 2 of the experimental mice injected with Gombe 2 venom died at different time points. One died after 30 minutes and the other after 1 hour, 30 minutes of venom injection. And lastly, one of the experimental mice injected with the Gombe 3 venom died after 45 minutes of venom injection. So that's the observed variation in survival time for venom challenge could be attributed to the possible existence of venom variants among the Bitis erectans venom sampled from the wild in state of northern Nigeria. And this could actually pose a challenge to snakebite therapy. Following the hemorrhagic activity assay, all the venoms were individually fractionated on analytical site exclusion chromatography to guide toxin classification and extracellular vesicle enrichment. So these are chromatographic profiles for the venoms from the Katsina state. These venoms actually show distinct chromatographic profiles, with toxins eluting at similar time, but with different peaks, suggesting differences in composition of each toxin. As you can see, the height of some peaks varies between venoms, which actually indicate quantitative differences in toxin expression levels. And so the gel panels you are seeing here are SDH separation of proteins contained in protease-enriched fractions. These are also chromatographic profiles from venoms from the Yobe state. They are also unique and distinct from each other. And lastly, from the Gombe state. So all the site exclusion chromatographic fractions from the individual venoms were subjected to enzyme activity assay, and protease-enriched fractions were identified. So panel A shows the identified protease-enriched fractions from the Katsina state. So fraction 1 was identified as protease-enriched for Katsina 2 venom. Fraction 14 for Cas9-3 Venom fraction 5, for Cas9-4 Venom, and fraction 11 for Cas9-5 Venom. In the Yobe state, fraction 1 was found as protease enriched for Yobe 1 Venom, fraction 3 for Yobe 2, and fraction 5 for Yobe 3. Lastly, in the Gombe state, fraction 2 was identified as protease enriched fraction for Gombe 1, fraction 9 for Gombe 2, and fraction 8 for Gombe 3. So the identified protease enriched fractions were subjected to AZ split analysis, and the gel panels I showed previously. This shows the AZ split separation of proteins contained in the protease enriched fractions. So the nature of proteases expressed in the identified protease enriched fractions were actually determined by performing protease inhibitory activity assay in the presence of specific protease inhibitors, such as PSMSF, which is a serine protease inhibitor, antipain, which is a cysteine protease inhibitor, and 1,10-phenolphthalein, which is a metalloprotease inhibitor. The results reveal that serine and cysteine proteases were the most dominant class of proteases in the Yobe state protein-enriched fractions. And then in the Gombe state, serine proteases were identified. And lastly, in the Cas9 state, serine and metalloproteases were identified as the dominant class of proteases in the Cas9 state protease-enriched fractions. So we went on to isolated and characterize Bitis arrectant extracellular vesicles. And these vesicles were actually validated using transmission electron microscopy. And the electron micrograph you see here reveals structurally intact exosomes of Bitis arrectant venoms from the Yobe state. So those in yellow are isolated extracellular vesicles. And these are for the Gombe state. And lastly, these are for the Cas9 state. However, the density of the extracellular vesicles were very low, and so we couldn't carry out functional assay to identify the additional role extracellular vesicles play during envenomation. So we went on to screen a library of peptides, that's one of them, against the identified protease-enriched fractions to determine which of these peptides have protease inhibitory activities. And so this high-throughput screen revealed that peptide 11, 24, and 25 actually showed moderate inhibitory activities against protease-enriched fraction K2F1. So we went on to test these peptides in vivo to see whether we're able to neutralize the hemorrhagic effect, since Bitis arrectants are known for their hemorrhagic status. And so we pre-incubated these peptides with a protease-enriched fraction for 10 minutes, and the mixture was actually injected into experimental mice. So after 4 hours, these experimental mice were euthanized, and we actually excised the dorsal part of the skin to see whether these peptides have been able to neutralize the hemorrhagic effects. And behold, these peptides actually neutralize the hemorrhagic effect, that is peptide 11 and 25. So we can see for panel A, we can see that peptides pre-incubated with fraction K2F1 at a concentration of 1 in 1 neutralized the hemorrhagic activity of the venom, and also 1 in 10 neutralized. But when you come to peptide 24, there's still hemorrhagic activities occurring. But for peptide 25, at a concentration of 1 in 1, this peptide couldn't actually neutralize the hemorrhagic effect. But at 1 in 10, there's complete neutralization. So the ability of these peptides to neutralize the hemorrhagic activities of Bitis arrectant could be attributed to the capacity to counter-interact with serine and metalloproteases, which are known to cause hemorrhage, following Bitis arrectant envenomation. And so in summary, the profile Bitis arrectant from Nigeria actually reveals subtle and stark differences in protein binding patterns. And of course, as expected, the hemorrhagic status of the venoms were evaluated. So the strategy of decomplexation actually resulted in toxin classification and extracellular vesicle enrichment. And finally, the identified protein-enriched fractions were actually useful in screening candidate inhibitors in peptide library, which were 20 to 31 of them, and the subsequent identification of 3 of them, which had in vivo detoxifying activities. So I would like to thank my supervisors, Dr. Imran Amlabu, Professor Goita Mandari, the West African Center for Cell Biology and Infectious Pathogens, and the World Bank for funding this program while I was doing my master's, and the Francis Crick Institute Science and Technology Platform, all members of my former lab, protein expression lab, and that one directly. Thank you very much for listening. Thank you, Mike, for this invitation.
Thank you very much, Roland.
Yeah.
So, are there any questions? And if so, just unmute yourself and then you can directly ask the speaker. The first one is from Eric.
Yes, thank you for the great talk, Collins. I wanted to know if, because in the single state Venom samples, you had showed this really nice variation within the state. Do you, by any chance, know the sex and the age of the snakes the samples were taken from?
Yes, so we picked only males for now.
Mm-hmm.
We didn't.
Okay.
It was difficult getting the female, so we just went by what we had. So you could see that we got 5 of them from a different state and 3. So it was just a random collection as to when we see them. And because it's part of my master's thesis, I didn't want to waste time, because to get males and females would be something very difficult. So we just went in for only males as to when we saw them.
Okay, thank you very much.
Okay.
I also have a question
from Matthias. Yeah.
Yeah, great. I never know how to do the hand in the in the self view mode, but no, really nice talk. I really liked to see the differences between the various populations. It's really nice to see. I had 2 questions actually. You were mentioning that you used a proteolytic degradation assay. Could you tell a little bit more about the way that you did the assay? Is it a zymography based assay or is it a plate reader based?
So it's protease inhibitory activity assay. This is a plate-based assay where we use azocasin as the general protease substrate. And so you incubate azocasin with the fractions. And after some time, you add the protease inhibitors to see whether you'll be able to inhibit the specific proteases in the fractions.
Okay.
Yeah.
Okay.
So,
but then do you look at the turbidity of the of your mixture, or what is your readout of the protease assay? Because I'm doing the same type of assay, not the classic, with collagen and gelatin.
Yeah, so we actually have measured absorbance.
Ah, yeah, okay, okay,
perfect.
Yeah, okay, nice. And then my second question was if you could go back to the slides with the different sec chromatograms that you were showing.
Okay.
Because I saw some very similar peaks near the end of the chromatogram, but they had different. I think it's this one that I want to talk about. Yeah, because you see this really nice peak at the end, but it's not always at the same volume. Do you have an explanation for this? Because it looks like it's a similar toxin, or at least similar compound that is eluting at that point, but it's. So for your Gombe 2, it comes a lot higher volume. Do you know why?
Yes, so what we were anticipating that maybe we had this because of different expression levels of each toxin. That's what we are actually anticipating. Yeah, different expression levels of each toxin. So that's what we are actually trying to see whether it's actually the expression levels that is making them like that.
Okay, yeah, nice, thanks.
Yeah.
But it also looks like that you used a different gradient, right?
Yeah.
So for the beam, you choose the longer gradient than for A and C, right?
Yeah.
Okay. Any further questions? Else, I have one. So you showed the list of different peptides. How do you select the sequences? Are these known serine protease inhibitors, or have you an in-house library that you screened against it?
So are you talking about this?
Yeah.
Yeah, so what we did was we randomly, the aid of Biobasic Canada and USA, they actually developed this peptide for us. So we sent the sequences to them. So these are random peptides, random sequences that we actually got and subjected to Biobasic Canada for them to actually design this peptide for us.